Hello and welcome back to another video on our journey from primes to the Riemann hypothesis. Today, last time we looked at what a prime number was, a very basic introduction, and asked ourselves a really interesting question around why can't any number be a product? And that kind of took us to the definition, as it were, of prime numbers and why they stand out from normal numbers. Today we're going to ask ourselves another interesting question around, how many prime numbers are there? So let's dive in. So when we thought about the definition of prime numbers, we said, if two numbers can be multiplied together, like 3 times 4 is 12, then 12 isn't a prime. But 13 was, 14 isn't, 15 isn't, 16 isn't, 17 is. And we kind of think, does that definition help us understand or give some insight into how many primes there are? Now you might say, there's endless primes, they just don't run out. But you might think about it a bit more, and some doubt might set in, because you might think, if larger numbers have more numbers smaller than them, and therefore the chance of there being a combination of two factors making that number seems to be high or higher. That's a vague kind of intuition. Let's look at it another way. Let's ask ourselves, let's kind of go through this thought process. So if we say every multiple of 2 is not a prime, it can't be because 2 would be a factor. Every multiple of 3 is not a prime. So we're chopping out possibilities. So every multiple of 2 is not a prime. That just leaves the odd numbers. Every multiple of 3 is not a prime. Every multiple of 4 is not a prime. Every multiple of 5. And we keep doing this. So we seem to be chopping out possibilities. Does that mean eventually we've chopped out all the numbers after a certain point? After a certain point they just fizzle out because all these choppings out, this sieving, this filtering has kind of covered everything. That's an intuitive kind of thought, but actually intuition isn't enough to decide the matter. We need to be much more rigorous and formal about making a statement about whether the primes run out or not. So let's just restate that really important idea there. Intuition is not proof. Lots of examples is not proof. A proof is a watertight logical argument that leads to a conclusion that we can't argue with. Somebody else can look at the logical steps and not find fault in them, and therefore not be able to argue with the conclusion. That's what a proof is. So we're going to have to use some kind of proof, a logical argument, to show that there are an infinite number of primes, or there aren't. So let's do that. This is our first proof in some sense, so that's quite exciting. And actually the proof is from Euclid, so 300 years BC, so very ancient. So what we're going to do is, and so this proof is due to Euclid, so we're going to follow in his footsteps. So what we're going to do is actually start with the assumption that there are a limited number of primes, a finite number. We're just going to start with that assumption. We're not saying it's right or wrong, not yet. We're just saying that there are, 5 primes or 10 primes or 100 primes. There are n primes, and we can list them then. If there are a finite number, we can say 1, 2, 3, 4, P1, P2, P3, so 2, 3, 5, 7, and so on. As long as there are a finite number of primes, we can always list them. Great. Now what we're going to do next with this list of primes is multiply them together. You'll see why we do that in a minute. And we'll create a new number called x. So x is all those primes multiplied together. The first one times the second one times the third one up to the nth one. Now this x is not a prime number. It can't be, because the way we've constructed it is by multiplying whole numbers. It's full of factors like p1, p5, p4. Let's illustrate that idea. Although it might be simple, it might not be obvious to everyone. So here are just some primes: 2, 3, 5, 7. Let's just say that these are all the primes ever. There's no more. So we'll create a number x, which is 2 times 3 times 5 times 7. Now I can't do that in my head. 2 times 3 is 6 times 5, 30. 30 times 7, I'm going to have to cheat. That's 210. Now that's not a prime because it's got factors 2, 3, 5, 7. So 30 times 7 is 210. So it's clearly not a prime. Okay. That's just to illustrate what we've done there. Let's now make another number, y, in the same way, but this time we're going to add 1. Is this a prime? Now, we don't know the answer to that yet, but there are only two options. Option 1, yes it is prime, and option 2, no it is not prime. Let's just sketch out what we've done there just to be clear. So with this our example here, if these were the only primes, y would be 2 times 3 times 5 times 7 plus 1, which here is 211. But we're speaking more generally. There could be 10 primes or 100 primes. We're just saying there's a finite list. Now it looks like intuitively that if we add 1, it's not very easily divisible. Let's come back to that. That's just an initial observation. So we've said, is this a prime? And there are only two options, yes or no. Let's look at the yes option. If y is prime, we've just found a new prime that wasn't in the original list. So that would mean that our original list of primes wasn't complete. So that was a contradiction then. We said that there were, 5 primes or 10 primes or 3 primes or n primes. By constructing this y, if it is a prime, we've just found a new prime. So that original list wasn't complete. Let's think about the other option, option 2, that it's not a prime. If it's not a prime, then it must have factors from our list of primes. Let's think about what we just said there. Any number that isn't a prime has factors. That's its definition. Let's write that out. We'll just illustrate it with some examples here. 12 and 13. Now 12 is 3 times 4, or it's 6 times 2. So it's not a prime. It has factors. 13 is a prime, and therefore we can't say something times something is 13. Now why did we say if it's not a prime, it has factors which are primes? That's because when we break a number down into factors, we can keep breaking it down until we get the primes, because they can't be factored any further. So 3 times 4, that 4 is 2 times 2, which are primes. If that wasn't a prime, we could break it down even more. Now we'll come back to this idea next time. We'll look at it a little bit more rigorously. But for now, I think we can accept this idea that if a number isn't prime, if it's composite, it can be broken down into factors. That's why it's not a prime. And we can keep breaking those factors down until we can't break them down anymore, which means they're prime. So every number that's composite, that's not a prime, can be broken down into, a multiple of a combination of primes. So let's just go slowly again. We've said option 2 is not a prime, so it must have factors which are primes, and the only primes we're allowed are the ones from our list. That's what we started with. We said there are a finite number of primes, no more. That means that y can be divided by at least one of those primes exactly without any remainders. So let's write that out. We've said y divided by one of those primes, might be p1, p3, one of the other ones, is that y, which is this whole thing here, this thing here, plus 1, all of that divided by one of the primes, and it shouldn't leave a remainder. Let's write that out. So we said y equals p1 plus, or times, p2 times p3 up to pn plus 1. That's what it was. And we've said it has at least one factor. Call it pi. pi. And that can be rewritten as, just separate them off there, pi. Now this pi is one of those primes. Could be p2, could be p3, could be p7. It's just one of them. Let's just say it's that one. So that divides neatly without any remainders, but this one doesn't. 1 divided by any prime is not a whole number. That doesn't divide. 1 divided by 2, 1 divided by 3, 1 divided by 5, 1 divided by 7. These are always more than 2 anyway, more than or equal to 2. So that means, what does that mean? That means this y, we've just shown that it can't be divided by one of the primes. So we said option 2, it is not a prime, so it has to have a prime factor, but now we've just shown that it can't. It's a contradiction. So y can't be divided by any of the known primes. So y must be a new prime not on the original list again. Isn't that interesting? So what we've done, we've kind of started with an assumption that there was a finite list of primes, and we've followed the two logical paths from it and arrived at conclusions which say that that list of primes isn't complete. So both of these options tell us that the original list of primes is incomplete. That's the proof. Let's say that another way. No finite list of primes can be a complete list of primes, because by the constructions we did, we arrived at something that demanded there was going to be another prime. If no finite list of primes can be complete, that means there are infinitely many primes. Ta-da! Let's kind of, that might sound simple. We've tried to take very slow steps there, but let me draw a picture just to kind of illustrate that proof. So we started with the idea that there's a finite list of primes, p1 up to pn, and we said, well, if we construct something like y equals p1 times p2 times p3 pn plus 1, is that a prime? Is it a prime? Yes. Or is it a prime? No. There are only two options. Yes. If it is a prime, well, it's not one of those because it's bigger than any of them, because we multiplied it now to 1. It's bigger than any of them. So we found a new prime. So that wasn't a complete list of primes. If we entertained the other option and said, no, it's not, which means it must have factors, but we just shown that actually none of those primes can neatly divide this y. which means it's a prime from the perspective of having a limited set of primes. A new prime. New prime. So it's not a straightforward proof if you're only used to, I guess, sort of school mathematics, but hopefully the logic of what we've just illustrated here is clear enough. We've shown by contradiction that our starting assumption wasn't safe because it led to troubling conclusions. It led to this option here, which was a new prime, and this option here, a new prime, neither of them that were part of the original list. A proof by contradiction, and that's quite common actually. We'll come across them more. So just to kind of say that again more slowly, a normal proof starts with valid assumptions, takes logical steps from those assumptions, that foundation, and leads to a valid conclusion. That's a normal proof, if we can call any proof normal. A proof by contradiction starts deliberately with potentially invalid assumptions, unsafe assumptions, or assumptions we're not sure about, takes logical steps which are watertight, so those bits aren't in dispute, but reaches a conclusion that's invalid. And because we can see it's an invalid or inconsistent conclusion, we can then say, well, it wasn't the logical steps, it must have been the assumptions. So that's what we did here. We started with the assumption that there was a finite list of primes. Our logical steps were sane. The conclusion was, well, hang on, there's a new prime, which wasn't in the original list. So that's a contradiction because the original assumption said there were only n primes. So that's how Euclid did it, 300 BC. Simple in some ways. I knew we've talked a lot about it because we didn't want to lose anyone, but the more you kind of think about it and write it out yourself and illustrate it with pen and paper, you'll see it's actually quite elegant and simple and quite powerful. Now, I wanted to stop there, but then I thought, actually, in talking to kind of friends, we sometimes as we're learning mathematics, we sometimes are tempted to think that thing we constructed, P1, P2, P3 plus 1, is a way of generating primes, but that's wrong. We never said in our proof that P1, P2, P3, P4, Pn plus 1 is a prime. We never said that. We only asked what happens if we say it is a prime, assuming there was a limited set of primes. That's all we did. We simply asked what happens if we say it's a prime. We didn't say it was a prime. Let's write that out. Y equals P1, P2, P3, P4, Pn plus 1. It kind of looks like it should be prime because there's this kind of unusual 1 sticking out the end, which makes it feel like it's not going to be divisible by any number, because 1 divided by something is kind of a fraction. It looks like it. Intuitively, it might feel like that must be a prime, but it's not. And we can prove that this is not always a prime with just one counterexample. And here's the counterexample. 2 times 3 times 5 times 7 times 11 times 13. 1, 2, 3, 4, 5, 6 primes. Plus 1 is this number here, 30,031. And that's not prime because we can check. It's 59 times 509. It's not a prime. So although it looks tempting, it isn't. So I kind of fell for that when I was learning. But it's you can see why it's tempting, but it's not. Fantastic. So today we've done our first proof, an ancient proof that the number of primes is infinite. I hope you enjoyed that. If it's kind of new and kind of unusual, just go through those steps yourself with a pen and paper. Talk it through. I had to do that until it sunk in, and then suddenly it was, wow, that's really simple, really. Shocking. So have a go yourself. If there are any questions or any kind of uncertainties around it, get in touch in the YouTube comments, and we'll try and kind of answer those questions. There's a blog as well, which I'll link to in the comments, in the description, so you can kind of read more about it more formally and more slowly. Again, I'm not going to be writing in a way with using lots of jargon. The whole idea of this exercise, this project, is to simplify and make accessible some of these really cool ideas. Fantastic. See you next time. Bye.